Section 4.6, Applied Optimization. Now, back a couple sections ago when we were doing all our graphing, we made an increasing-decreasing chart. And from that increasing-decreasing chart, we were able to tell when something was a local maximum or minimum. That increasing-decreasing chart where we looked for changes, whether we looked for changes in the original function, changing from increasing to decreasing or decreasing to increasing, or that we looked for changes in the first derivative changing from positive to negative or negative to positive, what we were really using there was the first derivative test. And it was first derivative test that allowed us to classify relative critical numbers, that's what I meant to say, allowed us to classify critical numbers as relative or local maximum minimums. Here I have the word relative. Previously we said local. I believe your textbook uses the word local. Local, relative, all the same thing. But the first derivative test where we analyzed changes from first derivative from positive, negative, negative to positive, or when we extended that, the original function from increasing to decreasing or decreasing to increasing, that was the first derivative test. And that's what we were using to classify critical numbers as maxes or mins. And the first derivative test was really very useful when we were sketching graphs, because it gave us that nice information. When we extended it to increasing, decreasing, it gave us that nice information about when a function was increasing or decreasing. But there is another way to classify critical numbers that I skipped then that I'll pick up now, and that's the second derivative test. Let C be a critical number of function f of x such that f prime of c equals 0. There's the first drawback to the second derivative test. The second derivative test isn't going to work on all types of critical numbers. Remember, there are two types of critical numbers. Critical numbers that come from when the derivative is 0, and critical numbers that come from when the derivative does not exist. So there's one big drawback about the second derivative test. It doesn't work on all critical numbers. If you have a critical number that comes from the case of the derivative not existing, you have to go back to the first derivative test where you look at those changes of the first derivative changing from positive, negative, negative, positive. Okay, so that being said, let C be a critical number of a function f of x such that f prime of c equals 0. If f double prime of c is less than 0, the second derivative is negative, then there's a relative maximum at x equals c. If you like the word local, local maximum. If f double prime of c is greater than 0, the second derivative is positive, then there's a relative minimum at x equals c. And 3, if f double prime of c equals 0, no conclusion may be made. Maybe you have found an inflection point, maybe not. You just don't get to say anything. And if you really have to classify that number, you have to say that that critical number c leads to a local max, local min, or nothing. You got to go back to the first derivative test. So if the second derivative is less than 0, you found a relative maximum. If the second derivative at c is positive, you found a relative minimum. That seems like it's working a little bit backwards to what you'd anticipate until you think about it in more detail. And I should have given myself more room over here. Second derivative negative. So I'm gonna run out of room, so I'm gonna change that to symbols there. F double prime less than 0, second derivative, means we're concave down. And so it's going to look something like that. If I have a critical number, if that's my critical number, let's say that's C, the picture has to look like that. And so it has to be a local max. And so that's what the second derivative test is looking for. It's looking at the concavity. And if my second derivative is negative, it means I have to be concave down. And so my critical number is a critical number. So critical numbers can lead us to local maxes, local mins. So it is a critical number, and it has to be sitting on a concave down curve when my second derivative is negative. And so it is a local max. The flip side, f double prime of x f double prime greater than 0, well, that's concave up. And so that means the curve looks something like that. If that's my critical number, there's my critical number C, it has to be a local minimum. And so what the second derivative test is really saying is, okay, I have a critical number, and it's sitting on a concave up curve, so I had to be a local minimum. I have a critical number, it was sitting on a concave down curve, it has to be a local maximum. So if you really get into it and really visualize what's going on, it isn't working backwards. But many times students just need to remember that a negative means you found a max, and that feels a little backwards. Positive means you found a minimum, a little bit backwards. But in reality, if you think about the pictures, it makes complete sense. So that's what the second derivative test says. Now, how to use the second derivative. 1, find the first derivative. Can't get to the second derivative without the first derivative. 2, find the critical numbers. 3, find the second derivative. 4, substitute each critical number found in the second derivative and classify if possible. A, if the value of the second derivative is positive, you have found the location of a relative minimum. B, if the value of the second derivative is negative, you have found the location of relative maximum. If the value of the second derivative is 0, no conclusion can be made. And if you need to really classify that one, you'll have to go back to the first derivative. That's kind of the increasing, decreasing chart. Note, the second derivative works backwards to what you'd expect. And we already kind of went into that. That if you think about the pictures, no, it doesn't. But a lot of people don't think about those pictures. A negative result means you found a local maximum. A positive result means you found a local minimum. Find the local extreme of the function. Use the second derivative test if applicable. So first I find that first derivative. 3x squared minus 6. Critical numbers. Let's make that legible. Set the first derivative equal to 0. So I get x squared equal 2, x equals plus or minus the square root of 2. Do not forget that all-important plus or minus. When you're solving an equation and you take a square root, even root of both sides, you've got to include that plus or minus or you're leaving off half the answers. It's not a small mistake. 3, second derivative, and there was my first derivative, so second derivative easy enough, 6x. Then 4, I plug in my critical numbers. So I'm going to plug in x equals square root of 2. That's 6 square root of 2. Now I don't particularly care what the number is. All I care about is that's positive or negative. That's greater than 0. It's positive. So at x equals 6 square root of 2, I have a local minimum. And if you needed the y coordinate, with y equal f of 6 square root of 2, you plug into the original function. And we're going to go ahead and simplify that and see what we get there. Just for the practice. So 6 square root of 2 would be this. 6 square root of 2, or 6 square root of 2 cubed would be 6 square root of 2, 6 square root of 2, 6 square root of 2, minus 6 square root of 2. Just for the practice here. 6 times 6 times 6. Going to need the help of my calculator there. Except I'm doing this all wrong. Let's pretend that that didn't happen. That's all wrong. The 6 square root of 2 is the value of the second derivative. It's not important at all other than it was positive. And this is a common mistake, so it's okay that I made it. We'll pretend I meant to make it. We have a local minimum at square root of 2. So pretending none of this happened, or no, I did it on purpose so I could talk about this mistake that's common. Yeah, you can believe that. If you're a little bit gullible, you'll pretend that I made that mistake on purpose. So just reiterating that 6 square root of 2 has no meaning other than it's positive. It tells us about the x equals square root of 2. That's a local minimum. And then my y coordinate comes from the original function. And this will be a whole lot easier to simplify. So square root of 2 cubed, showing way more detail than I'd expect of anyone. Square root of 2 cubed means square root of 2 times square root of 2 times square root of 2. If I put two of these together, square root of 2 times square root of 2 would give me 2 square root of 2 minus 6 square root of 2. So negative 4 square root of 2. So the point square root of 2, negative 4 square root of 2 is a local minimum. Moving on to another piece of paper to do the other one. So now we have the answer for what's going on at x equals square root of 2. For x equal negative square root of 2, f double prime of negative square root of 2 would be negative 6 square root of 2. That's less than 0. It's negative. And so that tells me at x equal negative square root of 2, we have a local maximum. Works back, if you're only going to think about positive and negative issues, works backwards to what you might feel should be. A negative result means I found a maximum. With y equal f of negative square root of 2. And remember, y coordinates always come from the original function. And so I have negative square root of 2 cubed minus 6 times negative square root of 2. So that's negative square root of 2 times negative square root of 2 times negative square root of 2 plus 6 square root of 2. You can't see that. There we go. Multiplying two of those together, that's going to be 2. The two negatives will make it 2, but then I have another negative there. So I'm going to have negative 2 square root of 2 plus 6 square root of 2 for 4 square root of 2. So the point negative square root of 2, 4 square root of 2 should be a local maximum. And then, as always, these picture things you can check. Now, I still have not put batteries into this calculator, so we'll see if it's going to work. I have my doubts. So, putting the original function in there. Actually, I brought batteries for it today, but I brought the wrong size batteries. We will try again tomorrow. So I've got the original function in there. I'm just going to hit zoom 6 because we don't have a lot of good information here. So we'll just go with the standard window, and then we'll fix it up if we need to. And that's actually a decent enough picture. Now we said, we'll go with this last one that's covered up here. We said that there's a local maximum at negative square root of 2, 4 square root of 2. So we'll do a trace. And then negative the square root of 2. And you can just put that in the calculator. Enter. And indeed, it goes right up to the maximum. So I feel very good. I did not change my 4 square root of 2 to a decimal. Now let's zoom in here and see what we got here. Okay, it tells me that the y coordinate here, zooming in a little bit more, tells me that the y coordinate here is 5.6568. We said that that really is 4 square root of 2, 5.6568. And so this absolutely checks. Again, remember, you can check these things by looking at the pictures and then doing traces. And so we did the negative square root of 2, trace square root of 2. And indeed, it goes to the local minimum, and it confirms that y coordinate. Got a few moments at the end of a test or quiz, check these things. Into the first video.